Okay, so we have the AES system, we have the SI system. We know what those units are. They're kind of a confusing unit. Because they're a confusing unit, there's another thing that we use called the radius of gyration. The radius of gyration is equivalent to mass moment of inertia. It's just a more convenient way to think about it. The radius of gyration says that if I do I equals mk squared, k is radius of gyration. Great name, by the way. Sounds like a band or something. So the radius of gyration can be solved for. It's equal to I over m square rooted. That might seem a little funny to start off with, but let's plug in some units. We just said that in the SI system, I is going to be kilogram meters squared. So this would be the square root of kilogram meters squared over kilogram. Right? Got a cancellation, square root of meters squared. Units are meters. So the radius of gyration is a way of doing two things. First off, giving resistance to rotation regardless of mass. I'll say that again. Resistance to rotation regardless of mass. Okay? So mass is a part of resistance to rotation, but so is shape. The shape of an object, regardless of its mass, is a resistance. It's a resistance because either the components are close to the center of rotation or they're far away from the center of rotation. So there's a way to talk about radius of gyration with actually dividing by the mass. You can have a really heavy object and a really light object have the same radius of gyration. Also, it's in meters. So in meters, that we can kind of relate to that a little bit better. What it actually means is it means the radius of an object that is a thin shell that would have the same moment of inertia as this object. I'll say that one again in a minute. I'll just let you chew on it for now. Okay, so we have our equation. We now might want to relate this to something that we can actually calculate. If we knew the mass of each little particle throughout an object, yeah, we could take the integral and add up all those little particles. But typically we know more about the shape than the mass, and we assume that there's a constant density for most of the problems that we have. So how do we relate mass and volume? What's the relationship between mass and volume? Density. Density is equal to what? That's right. Mass per unit volume. How much mass we have per unit volume. If we have a little tiny piece of mass and a little tiny piece of volume, we get that it's equal to dm dv. If I multiply the dv on the other side, I get the equation a little piece of mass is equal to rho dv. I can go ahead and plug that into my equation over here and say, well, moment of inertia is therefore equal to the integral over the volume of r squared rho dv. If the rho happens to be constant, that means it comes out of the integral sign, and we could say it's rho times the integral over the volume of r squared dv. That allows us to find the moment of inertia of a shape by knowing the volume of it, and then multiply it by the density to find the total moment of inertia. Any questions about that? You sure did, yeah. Okay, right. You remember the shell method? And yeah. So the next slide is the shell method and the disk method, which you learned in Calc 4, if you've taken it. If you haven't taken it, it's back. The shell method and disk method are actually, they're shortcuts that you don't need if you've been through the whole calc sequence. If you've been through the whole calc sequence and you can do, what do they call it? Multiple integrals? Triple integrals, thanks. If you can do a triple integral, you don't need the disk or the shell method. The whole purpose of the disk or the shell method is to take a triple integral problem and turn it into a single integral problem so that we can teach dynamics with only a prerequisite of Calc 1. Okay? That's the reason it's here. It's a very useful skill because maybe you'll forget how to do triple integrals one day. But if you do know how to use triple integrals, you can do that and you'll get the same answer. However, we're going to use the shell method and the disk method. And it really helps because the disk method helps us explain some of the concepts of moment of inertia. So we have this object here, this dome. And we want to be able to find out, well, what is the integral r squared dv? And then we're going to multiply that by rho, and that's going to be equal to our I. That is our goal, is to find the moment of inertia of the object. The very first thing we're going to do is say, well, we need to know something about dv, this little piece of volume. We can choose the type of dv we want. Yeah, go ahead.
So, I'm just wondering, do we move everything to one side, or is that, I'm thinking of this 2 steps ahead, or I'm thinking.
Okay, I'll get there.
Okay.
Okay, so r squared is going to be, most of the time that's going to be given, or we're going to be able to find it with the information given. But this dv, we need to be able to add up every little piece of dv throughout the object. What we can do to make this a single integral is we can look at either a whole bunch of little rings that are going to start as little tiny rings in the center that look something like that, and then they're going to get bigger and bigger and bigger and bigger until we reach the outside of the object. If we do that, that sweeps through the entire volume of the object. And I'm sorry, I made a mistake there. The first inside ones are going to be all the way to the top and all the way to the bottom. That would be the first ring, or the first ring would just be barely around the axis. It would just look like a line, like that. And we get another ring, and another ring, and another ring. We're going to add all of those rings up until we get the full volume of the object. So all we have to do is we have to figure out what's the volume of that little tiny thin strip of ring. You need to figure out what dv is. If we look at this little thin strip of ring that we have, it can be helpful to basically cut it. I'm going to get out a hacksaw, I'm going to make a cut on it, and I'm going to spread it out into a big flat plate. Okay, I got a nice big flat plate. What is the width of the plate? Well, let's do the easy one first. What's the height of the plate? Z. Very good. We got a Z there. What is the width of the plate? Close. It's this. It would be the circumference, right? Which is 2 pi r.
Did you take a slice down the middle of the object, or what did you do?
Well, I need a piece of paper to show you properly.
You unrolled it.
Yeah, so I have this piece of paper, and it's a shell. And I just cut it and went like this. So the width of it is actually going to be the circumference of that circle, which is calculated with what? 2 pi r. What is r in this case? The radius of the circle would be y, right? 2 pi times y would be our width. 2 pi times y would be this. And then finally we need the thickness. What would the thickness be? Well, that one's kind of tricky, but it's actually written right here. It's just going to be a small change in y, right? Because there's a little bit of a thickness in y. So that thickness here is going to be dy. Now, of course, with the volume, we're just going to multiply those together, and we end up with 2 pi y. 2 pi yz dy. 2 pi yz dy. Yeah, I got them all. Okay, so a little tiny dv is going to be equal to 2 pi y z dy. What is going to be our r in this case? No, not our. If I draw just a little shell, and we look at the radius from that center, the iz axis, to the edge of the shell, it would just be y. So r equals y. And dv equals 2 pi yz dy. Just got to plug those in now. I is going to be equal to density times the integral of r squared, which is y squared, times dv, which is 2 pi y z dy. And I end up with I is equal to 2 pi is constant, so I can take that out. 2 pi rho times the integral of y cubed z dy. Okay, I need to integrate this with respect to y. That's going to be really easy for the y, not so easy for the z. This is where the equation of that shape would come into play. Somewhere in the problem, they would tell you z is equal to y squared or something like that. And then you plug that in, and then you take the integral. Does that make sense? You need to draw your shapes of integration. You need to draw your shells or your disks. It's the only way you're going to answer these questions properly. So make sure on all of your written homework you are drawing your differential element, whether it's a disk or a shell. The disk has a little trick to it. In the disk element, we're going to do the same thing to start off with. We're going to figure out what is the volume of this little disk that we can create. And basically, if you want to picture this, we would start at the top, and we'd have the little tiny disk that looks like this. And then we'd have a bigger disk. Then we'd have the one that they drew all the way down until we have the full disk on the bottom. And all of those disks added together are going to give us the full volume of this object. If we use our I equation, it's going to give us the full moment of inertia of this object. So what would dv be in this case? We have a disk. What's the area of the top face of that disk? Pi r squared. Pi r squared. And what would r be? No? Oh, that's the width. I asked what r would be first. Yeah, r is y, so that's equal to pi y squared. And then the second question that Raymond answered was, what's the thickness? Well, thickness is a small change in z, or a dz. So to get the volume, we just get pi y squared dz. Okay, this is where the trick comes into play. Not all objects have the same moment of inertia. Okay? If you notice the thin ring on top, all of the stuff, every part of that ring, and each ring that we add up is equidistant from the axis of rotation, the axis that we care about, IZ, right? Every piece on this ring is the same distance from that axis. Is every piece on this disk the same distance from this axis? If I were to draw a little dot shoot, oh, here it is. If I draw a little dot, is that on the disk? Is it the same distance from the z-axis as this dot? No. Say it again. Exactly. They can only be on the outside ring. And every ring we have, each piece of that ring is equidistant from the axis we're looking at. However, with the ring, that's not the case. So now what we need to do is we need to actually consider a small piece of moment of inertia about the z-axis. A small piece of moment of inertia, this is where we're going to introduce composite bodies. We're going to introduce the idea that certain shapes have given equations for a moment of inertia. I just have the textbook here. I'm looking at the 14th edition. And I'm going to look at the back of the book. Oh, okay. This is the ones you said is big. So if I look at a disk. Okay, so notice that there are different ones. There's an IXX, an IYY, an IZZ, and an IZ prime, Z prime. What that's telling us is which axis it's taking the moment of inertia about. The XX just means I'm taking it about this x-axis right here. YY, notice that those are equivalent in this case. The IZZ is the one we want to look at. 1/2 mr squared. The I z prime would be an axis that's on the edge of that over there. Okay, so what we want is 1/2 mr squared. I do want to send out a little warning here. There are editions of this textbook with errors in the back. I believe edition 12 has an error, and I think edition 13 may as well. If you have edition 12 or 13, I can either give you a copy of this, or if you have a chance to just compare it to my book and make a few, corrections to the back. Yeah?
For the test, should we try and fit like all of these on our note sheet, or will we have like a stage to print out of these?
Good question. So if you need one, I will put it on the test.
Okay.
But I generally don't put it next to the question. I put it on the front page of the test, so you have to know to go look at it. But yeah, you don't need to put these on your note sheet. Okay, so this is a thin circular disk. That's what we're using for our integration. So if we go back and look at our equation, we're going to have to say that for each little piece of moment of inertia, I expect it to be equal to 1/2 r squared dm. I got that right out of the back of the book. It said that the thin circular disk is 1/2 mr squared. The only difference is I put a dm because it's just a little tiny piece of moment of inertia. Does that make sense? Okay, with that, now I take the integral of both sides, and I have a 1/2 that wouldn't have been there otherwise. So when I take the integral of both sides, on the left-hand side, I get I, the moment of inertia about the z-axis, and that's going to be equal to 1/2 times the integral of r squared dm. Notice how that is a different equation than what we used for our initial moment of inertia. Why? Because we're using the disk method. And then we would take that out. We'd say, well, Iz is equal to 1/2 times rho, we're assuming a constant density, times the integral of r squared dv. And then we would plug in our dv. We would say that's equal to 1/2 rho, the integral. R in this case is y again, so we'd say y squared, and dv would be pi y squared dz. And we get 1/2 rho pi integral y to the 4th dz. Now we would have to substitute in an equation for y that has a z in it so that we can take the integration. Any questions about that part?
So when you switch from the dm to the dv, you just add the rho.
Yep, because rho dv equals dm.
Okay. And the rest you just plug in a.
Plug this in
Yeah.
for dv, and I plugged in y for r. So I just plugged in two things. Okay, the next thing we want to introduce about moment of inertia is the parallel axis theorem. This is the one Raymond hates, right?
Yes.
Okay. There's nothing wrong. This is actually, if you can get it down, most of it's just record keeping. Okay, so how do we do this? Well, we can use the back of the book, and we can look up particular different shapes. And if we want to combine those shapes together, we can actually find the moment of inertia of a composite body, a body made up of multiple shapes that can be added together. However, you can't just take two moment of inertias and add them together if they are about different axes. You can only add two moment of inertias together if they are about the same axis. However, there's the parallel axis theorem. The parallel axis theorem states, if you can find the moment of inertia about any given axis on a rigid body, you can find the moment of inertia about another axis using the parallel axis theorem. Typically, how it's written is the moment of inertia of a point is equal to the moment of inertia of the center of mass, which they use G for center of gravity. Center of mass and center of gravity is the same as long as we have a consistent gravitational field, which is a pretty good assumption here on Earth. But if you were dealing with planets or very large, asteroid belts, that wouldn't be the case. And then we're going to add on to it md squared. M is just a mass of the object, and d is going to be the distance between the two axes. Now, you might be confused initially with the idea of these two axes. When there's a 3D drawing, it's pretty easy to tell that they're axes. Like, for example, this one and this one are two axes, and they are parallel to each other. However, if we were to looking at that object straight on, it would just look like a point. This would be the z-axis, and this would be the z-prime axis, and d would be this distance between the two. Does that make sense? Let's see if we can prove this one real quick with the parallel axis theorem. We know that the moment of inertia about the center of mass of a disk is 1/2 mr squared. That is the center of mass, so we'll call that Ig. Ig is equal to 1/2 mr squared. I z prime z prime, that's going to be equal to 1/2 mr squared, which is this moment of inertia about the center of mass. Then I'm going to add on to it m times d squared. D is the distance between those two parallel axes. What would that be for this particular disk? The distance between that point and that point would be r. So let's plug that in. And we end up with 1/2 mr squared plus mr squared, which is the same thing as 2/2 mr squared, which equals 3/2 mr squared. And you notice that that matches what's shown up here. So the parallel axis theorem is taking a moment of inertia of a body about one axis and moving it to another axis. Any questions about that? I was hoping for 2 example problems. We might be able to just get through this one, and then I'll have to do a composite bodies example problem as a watch-at-home video. We're going to do this one really quick. This is 17.7, page 405. Unfortunately, I didn't write down what it's asking, but I believe it asks us to find the... here it is. It says, the solid is formed by revolving the shaded area about the y-axis. Determine the radius of gyration, ky. The specific weight of the material is gamma is equal to 380 pounds per cubic feet. So we can say given gamma is equal to 380 pounds per cubic feet. I'm going to warn you, you really need to pay attention to units in all of these problems. Notice that that is a specific weight. Yeah, it's a force per given volume, not a mass, not a force per given mass. I'm sorry, not a mass per given volume. It's a force per given volume. And then we have to determine the radius of gyration. Does it tell us anything else? Not really, but I can pull from the drawing that y cubed is equal to 9x. And we're supposed to find, and I have 4 minutes. We're supposed to find ky, okay? So I am going to go a little bit fast on this, but remember you can always watch it when you get home again. The reason I'm going to go fast is because you're almost out of class. This is a disk method. With the disk method, we said that we're going to draw a disk. By the way, you could use both on this one. There's not really one that's better. Typically, I look at what my d is going to be. This is going to be a dy. And I notice that I have a y cubed. So it's going to be pretty easy to differentiate in terms of dy. Okay, if I do the disk method. If I were to do the shell method, I'd have a dx, which I could also use. So both of them work. I think in this case the disk method's a little bit easier. We know that a little piece of that volume is going to be the area, which is pi r squared, times the height. The height is a small change in y, and my r in this case is just going to be x. So I'm going to have a little piece of volume is equal to pi x squared dy. Yeah, so I have to remember that a little di is actually equal to 1/2 r squared dm. And when I take the integral of that, I get that I is equal to 1/2 times the integral of r squared dm. I need a 1/2 out here. And now I can put in the x for r squared. R is equal to x in this one. So I have I is equal to 1/2 times the integral of, I'm going to take my constants out, rho pi, the integral of r squared is now x squared. There's another x squared, so that's x to the 4th dy. Okay, so I now know that I have my equation, and I know, given up here, y cubed equals 9x. If I solve for x, I get that x is equal to y cubed over 9, and I can put that in. I is equal to 1/2 rho pi integral of y cubed over 9 to the 4th dy. Okay, I can pull that 9 to the 4th out, and I end up with 1 over 2 times 9 to the 4th rho pi integral y to the 12th dy. Any questions about that part? Okay, so now all I have to do is solve the integral. I'm going to have y to the 13 over 3. I'm going to say that I is equal to, I need my limits of integration too. My limits of integration, I just look at the picture. 0 to 3. I'm starting at 0, I'm going to 3 in the y direction. So I'm going to have 0 to 3 on my limits of integration. And that's going to be equal to 1 over 2 times 9 to the 4th. Oops, that 4 should be on exponent. Rho pi times y to the 13th over 13 from 0 to 3. Now you get your calculator out, and you get 29.362 times rho. Okay, so we're almost there. But that gave me the moment of inertia. I could figure out my rho from my given 380, from my given specific weight. But that's not what it's asking for. It's asking for ky, which is the radius of gyration. So how do I find that? I equals mk squared. Good.
So with your density and the I, you can solve for k by the
It's even easier than that, though. We don't even need density in the end. So we know that I equals mk squared. Solve for k. K is going to be equal to I over m times, or square rooted. We have I, now we just need m. How would we go about finding m? No, that's not going to give us m. But we don't know the volume. We're not given a volume, right? Well, m is just equal to the integral over the mass dm, right? If I take the integral of dm, I get m. Well, I can do everything I just did up there by plugging in for dm. So my mass would be equal to the integral. Now I just plug in my value of dm, which is equal to rho dv, and dv is given up there. So I end up that m is equal to the integral of rho, which is constant, times dv, which is pi x squared dy. We do the integration again. We plug in our value for x, which is y cubed over 9. We integrate again. We get an equation that tells us mass in terms of rho. In this case, the answer ends up being mass is equal to 12.117 times rho. And then we just say ky is equal to the square root of I, which we found is 29.362 rho over 12.117 rho. Our rho's cancel out, and we end up with a ky of 1.56 meters. Notice how the density was not even needed to solve the problem. So the density of the object does not affect the radius of gyration, because the radius of gyration just cares about shape. It would affect the moment of inertia.